All right. Good morning, everybody. Welcome back. Quick announcements before we start the lecture. So we will have in-class assignments this coming Friday. For the in-class, I have to be here, but if you don't want to come to the classroom, that's fine, okay? And the solution, if you are here, you can hand me the paper. If you are not, then just use Canvas. If you come here, you are free to discuss with your colleagues, okay? And I will be here if you have any questions. Second announcement, there is homework due on Thursday night. Okay? So do not forget about it. If you already did it, then you are good to go. Okay? All right, so let's recap where we left last week. So the last part of the lecture was regarding acids, and I presented you two different classes of acids. First was hydroacids, which are composed by hydrogen plus an element from group 15, 16, or 17. And then the second class of acids are the oxoacids. Okay? So now we have hydrogen, an element from groups 13, 14, 15, 16, or 17, and oxygen. Okay? So that's the only difference between hydroacids and oxoacids, the presence of oxygen. And we talked about nomenclature of hydroacids. First word, first part of the first word, you are going to use the word hydro. The second part, the name of the parent element with the end changes to IC. And then the second word, acid. So do not use the prefixes mono, di, tri, or tetra to indicate the amount of atoms when you are naming acids. Okay, so for today, let's tackle oxoacids. Here, the nomenclature is a little more complex, so let's go through the rules. First word, first part of the first word. The second part of the first word is the name of the parent oxoanion, okay, the XO part, except that the ending is changed to IC. And then the second word is acid. Therefore, we are going to use first the name of the parent oxoanion, XO. The ending is going to be changed to IC, space acid. Okay, so let's see. All right. So I hope people on Zoom can see that. No, they can see it. They should be able to do so. Okay, so to remember the most common oxoanions, we can use the lipdecano. Okay. So lipdecano 881 super infinite. The underlined letter represents the symbol of the first element in the oxoanion. So starting with me, the underlined letter is for nitrogen. The number of consonants represents the number of oxygen atoms present in the oxo onion. So for me, we have 3 consonants. So therefore, NO3. Because this is an ion, it has to be negatively charged. And the number of vowels represents the number or the magnitude of the negative charge. For Nick, we just have 1 vowel. Therefore, the charge of NO3 is 1 minus. And the name of this oxo onion is nitrate. So let's do camel as a second example. Underline the letter C for carbon. Number of consonants is going to be the number of, the number of oxygens is going to be the number of consonants. So we have 3 consonants, so therefore CO3. In the charge, the negative charge of the CO3 is exactly the number of vowels, in this case 2, so therefore 2 minus. The name of this oxo onion is going to be carbonate. Okay, so every time we have the oxo onion, we have to finish in ATE. So I will put this on canvas, and then you will have it for your record. Okay, so using the camel, it's a very simple way to remember all the most common oxo onions, the ones we are going to use the most, and the formula of the oxo onions. Any oxo onion can react with hydrogen. So hydrogen is going to neutralize the negative charge, and that's going to form an oxo acid. Nitrate, 1 minus charge. We need 1 hydrogen to neutralize the charge, and we are going to form the oxo acid HNO3. And the nomenclature of this oxo acid is going to be the following. First, the name of the oxo onion. We are going to remove ATE and add IC. Nitric. Okay. We changed the ending here. And then leave a space, acid. Okay. Therefore, HNO3 came from the nitrate ion. Therefore, this is the nitric acid. For carbonate, 2 minus charge. This is going to be neutralized by 2 hydrogens. So we are going to get H2CO3. Nomenclature. Carbon and the enzyme IC, carbonic. And then acid. Okay, so start from the oxo onion. There will be negative charges. Those negative charges will be balanced by adding hydrogens, and then you have the oxo acid. And then the nomenclature, first part of the word, ending in IC, space acid. Okay, so nomenclature requires a little bit of training. So we are going to go through a blend of examples to make sure we have everything squared off. So I showed you the camel to help finding the standard. I showed you the nomenclature for H2CO3. So let's take a minute and think about the nomenclature for H3PO4. Then I will go with you guys and we will move on. Okay, so H3PO4. PO4 comes from Phoenix, starting with phosphorus, 4 consonants, 4 oxygens, 3 vowels, 3 minus charge. And this oxoanon is phosphate. Attention here, ending in ATE. To move from the oxoanon to the oxoacid, we are going to balance the negative charges by adding hydrogens. 3 here, we have to indicate 3 as a substrate. So therefore, H3PO4, that's the acid that we want to know the name. Nomenclature. Replace ATE by IC, phosphoric, and then second word acid. And that's how you name H3PO4. Okay, very good. So Michelangelo will give you the standard for oxoacids. However, some oxoacids can have more or less oxygen atoms than the standard. For example, chloric acid, HClO3, can add or lose oxygens. And once you add more oxygen atoms or lose, you have to change your nomenclature to reflect that you are changing the formula. So we always start with the standard. In this case, HClO3. And from there, we are going to, for example, add 1 oxygen to the structure. So when we add 1 oxygen to the structure, that becomes HClO3. HClO4. To reflect the change in the formula, we need to change the nomenclature. It's going to be a very minor change. So we are going to add per in front of the name. So this was the chloric acid, adding one oxygen, this becomes the third chloric acid. So that's the change that we are going to make. And it's possible to go in the opposite direction as well, losing oxygens. So from the standard, we can lose one oxygen, and this becomes HClO2. The change in the nomenclature is going to be in the oxoanion name. So instead using IC at the end, we are going to use OUS. So that's going to become the chlorous acid. Here is where we changed. And it's also possible to lose two oxygens from the standard. Losing two oxygens from the standard, that becomes HClO. Now we are going to add hypo in front of chlorose. And then acid. Yes.
Can you ever have two extra oxygens?
No. Yes. Yes, it's a special case. We are not going to cover in the course.
Okay.
Okay, so it depends on two acids combining together, and that becomes another topic. Phosphorus can do it. Okay, the phosphoric acid can do it, but we will not cover it. Okay, so this will cover everything we need to know. Okay, so the nomenclature here starts knowing the standards. You can use the panel, and from the standards, you gotta recognize if there is addition or if we are losing oxygen atoms, and with that, adjust the nomenclature. Okay. I'm tired. There we go. Seems like the camera likes you, huh? Okay, very good. So All right. Okay, so any acid can react with a base, and that's going to form a salt. So we are going to cover that later on. And salts, we already saw part of each. For example, sodium chloride, so very simple salt. Strontium iodide was the other example. But we can also have salts containing polyatomic ions. So because those ions are negative, they will attract cations to balance the charge. And every time you have a cation and an ion, you have a salt. A polyatomic ion is any ion that has more than one element in its composition. Nitrate is a polyatomic ion because it's composed by nitrogen and oxygen. Phosphate is another example of a polyatomic ion. When we have salts composed by polyatomic ions, we are going to follow the same nomenclature as we already saw for ionic compounds. The cation gives the name of the parent element, and the anion gives its name as well. First example here, NaClO3. Okay. All right, so let's break this in two parts. ClO3 is a polyatomic anion and comes from ClO3 minus. And I'm going to just do an adjustment here. But between parentheses, the minus charge is for the whole thing. So this is negative. The name of this anion is chlorine. This negative part will attract a positive part to balance the charges, in this case sodium. We are going to cross charges here, one you don't need to represent, and this will form the compound NaClO3. Okay, so nomenclature of this compound, first is going to be the name of the cation, sodium, space, and then the name of the anion. Chloride. Okay, one thing to pay attention when you have the charge of the polyatomic ion is the charge for the whole thing. Okay? The whole thing will behave as a unit. And that's why we have Na2CO3. The charge for carbonate is 2 minus, as we saw here before. So I'm just going to put between parentheses to indicate that it's for the whole thing. carbonate needs 2 electrons, and each sodium can donate just 1. Remember, we saw that before. The strategy here is to cross the charges. So 2 will become the main number of sodium atoms, and for carbonate, you just have 1. So that's why we have these 2 here. Nomenclature, sodium, the name of the first element, and then carbonate. Okay, do you need one more example regarding this topic, or should I move on? Silence, that means yes.
An anion is just any ion that's negatively charged, right?
Say it again.
An anion is just any ion that's negatively charged.
Yes. And cation, the opposite.
And those things don't really exist naturally because they're attracted to positive charges, so they destroy
Exactly.
themselves when they exist.
Exactly. It has to be balanced somehow. Okay. Okay. So let's do one more example before we move on. So I will give you the name of the salt, and then I want you to do the opposite that I did before. Okay? So let's take a look at magnesium phosphate. Okay, so the first thing I want you to do is to figure out the charge for magnesium. So what's the charge for magnesium that makes this element stable? Magnesium belongs to the group number 2. That means 2 valence electrons. Now you have to make the choice. gain 6 to get to 8 or lose 2? Easier to lose 2, so therefore magnesium is 2 plus. Okay, so that's where things start. Now the second part in this kind of problem is to figure out the formula for the phosphate ion. Phosphate comes from phoenix. Therefore, we have P, always followed by oxygen. Number of consonants is 4. Number of vowels 3. And that's going to be the magnitude of the negative charge. Okay, so therefore, we have magnesium 2 plus, in other words, needs to lose 2 electrons, and each phosphate will acquire 3 electrons. Now let's combine these 2 ions. So always starting with the positive, followed by the negative. Because this is a complex oxo anion, I'm going to put between parentheses and indicate the charge on the outside here. The rule is to cross the charges. 3 becomes the number of magnesium ions. And attention here, the 2 will be outside of the parentheses. Okay, so when you have a complex or a polyatomic ion, you need to use the parentheses to represent the number of that ion that you have. Okay, so I would strongly recommend you to go back and take a look regarding nomenclature and how to draw the formula. You have to know it. You have to know it. And I will tell you one thing, as a friend, it's very tempting to Google these things. Guess what? You are skipping the process, right? So when you are Googling, first, you have no idea what you are looking for. So anything that Google speaks up, you will accept. Second, that will make you slow. And we are always in time crunches here. So you need to know at least how to look for things. Okay? So don't do it. Okay? It's fine to do at the beginning, but you have to get a grip of it. This will come back again, and if you don't know, it will hunt you all the way to the end of the semester. Okay? All right. Okay, so we covered a lot of ground here. I showed you 2 different classes of compounds. First one, ionic. Ionic compound, there is always an element losing electrons and another element accepting electrons. Ionic compounds, they can be salts, oxides, or bases. So we will go over bases in the chapter number 4. Covalent compound, we didn't talk in details about the bonding, but the bonding will be based on sharing of electrons. And again, here we can have oxides, acids, and what we call molecular compounds. Molecular compounds is any compound that's not an oxide, a base, an acid, or a salt. And therefore, this is an excellent time to introduce molecular compounds. Molecular compounds are very simple. As I said, any compound that's not a salt, oxide, or acids. Molecular compounds are usually formed between elements shown in green and yellow that belong to the groups 13, part of it, 14, part of it as well, part of the 15, 16, 17, 18 for hydrogen. The nomenclature is pretty simple, very similar to oxides. The first word is the name of the first element in the formula. And the second word is the name of the second element in the formula. And here you will have to use prefixes to indicate the number of atoms of each element in the molecule. Again, do not use the prefix mono with the first element. Let's tackle 2 examples here, starting with BCl3. First word is the name of the first element, boron. And then the second word is the name of the anion. So Cl comes from Cl minus. Cl minus is chloride. And because we have 3, we have to add the prefix trichloride. So every time in a molecular compound that you have Cl, that comes from chloride. It has to come from chloride. Okay, so therefore here for the second example, it's very, very similar. First element is phosphorus. Read it again. Cl always comes from chloride, but we have 5, therefore phosphorus pentafluoride. And that's how we are going to name molecular compounds. All right. Okay, so we have some time left. So let me start the next chapter. Okay, so next chapter, it's a very complex chapter, and we're going to spend some time in it, stoichiometry. Okay? So things will start to get a little more complex, and again, you need to know what we talked in the previous chapter, and we will build on that to move on into chapter number 3. We are going to start covering types of chemical reactions. After that, we will talk about mole, molar mass, and balancing chemical equations. And finally, limiting reactants, percent yield, empirical formula, and percent composition. So that is the goal for this chapter. So let's start with types of chemical reactions. In a chemical reaction, elements will combine with themselves or other elements, producing new compounds to achieve stability. Okay? So everything in a chemical reaction, the driving force will be stability. Systems will react to achieve higher stability. Everything before the arrow in a chemical reaction is labeled reagents or reactants. Everything after the arrow is going to be labeled products. The numbers in red are stoichiometric coefficients, okay, or the amount of the element or the compound. And in blue, we have the physical state of each component. Sometimes it's very easy to know the physical state, sometimes it is not. Okay, so therefore, I will not require you to represent the physical state. However, if you do so, that's a plus, and it's always good if you know it. Okay? If you know part of it, that's fine as well. Okay. There are 4 different types of chemical reactions. First one is labeled combination or synthesis. In this kind of reaction, we always start with 2 or more reactants, and we are going to form one product. Okay. Therefore, combination reaction start with 2 or more reactants and form one product. But this point doesn't matter why they do that. You need to be able to identify this kind of reaction. The opposite of the combination is the elimination reaction. In the elimination reaction, we are going to start with 1 reactant and form 2 or more products. It's also called decomposition. Single displacement. We are going to start with 1 element reacting with a compound, and we are going to displace one of the elements in the compound and isolate the other one. Okay? So in this case, element A is displacing B, forming AC, and ejecting B from the structure. And finally, double displacement. You're going to start with 2 compounds. And you're going to displace 2 things here. Okay? So A and B reacting with C and D. You're going to get AD. A displacing C, and then C will react with B, forming C.